The primary motivation for Project BANGOS is to provide a cello user with a tool to deal with the inherent variation in biology. Biology, even synthetic biology, must address uncertainty to see the fruition of successful applications. Optimization theory holds, whether linear or nonlinear, that a global maxima lies on a vertex, a peak, or an edge. This means an optimum may be sensitive to variation or uncertainty in the related constraints at the global optima. On screen, you will see common sources of biological uncertainty in synthetic biology and a visual reminder of what finding an optimum looks like in a high-dimensional space using a common algorithm. BANGOS hopes to aid users in addressing and understanding how uncertainty relates to common failure modes such as those described in the 2016 Science paper on genetic circuit design automation and how optimization is related to those. By providing a user with knowledge regarding uncertainty's impact on their design from cello and the selection and how that selects non-performance variables with performance variables from cello, they can understand how a design may succeed or fail in other areas, not just design performance. The core functionality has a user prioritizing and assigning weights to variables for cost, manufacturing, and circuit toxicity, along with the design constraints and variables. This is done by applying the design tool from cello, running through with cello inputs to create a design, and iterate through the parameters with stochastic simulation. This applies the values to an objective function to provide a relative score that would be used against other values run through the same tool, and then plots these devices' performance and their sensitivity to key inputs for genetic circuit operations. This allows the user to decide what next steps to take in the design process.
We are now going to go over the code behind BANGOS to give you a little more insight about how BANGOS constructs the objective function and scoring metrics. BANGOS first prompts the user with a welcome message as well as instructions to provide the weights for each metric BANGOS uses to calculate the BANGOS factor. These metrics include the cell performance, circuit toxicity, part manufacturing cost, and assembly cost. The weights are then normalized for them to sum to unity. Afterwards, the user is prompted for them to input the chases where the circuit is going to be built on, as well as the name for the circuit. Lastly, the last user input is to specify the number of input signals needed for that specific circuit. Then the cello query is called in order to get the best score as well as the best input signals. Then the cello query is called 5 more times in order to get an average score as well as a standard deviation. Then parameter perturbation is performed using a stochastic simulation of Gaussian noise, which is added to each parameter one at a time of the input signals in order to measure how robust each parameter of each input signal is when encountered with Gaussian noise in respect to the cello score. Then plots are performed where we can see the delta scores as well as the scores of each parameter perturbation with average score, standard deviation, and best score. If the score of the parameter perturbation is outside of the standard deviation range, it is considered to be very sensitive to noise and should be well handled. Afterwards, the teletoxicity is calculated as well as the part manufacturing cost. The part manufacturing cost uses items standard registry of biological parts in order to assess whether the parts used in the circuit exist. If the part exists, a cost of 0 is granted to that part, and if it does not exist, a cost of 1 is given. Lastly, the assembly cost, which relies on the GC content, is calculated by analyzing the GC content of each sequence in the circuit and then sum up. Then the objective function is set up with the weights inputted by the user as well as the metrics mentioned before, which are all normalized in order for them to sum to unity. Then a pandas data frame is printed on the terminal with the average score, the toxicity, the cost, the total GC content, as well as the objective function.
For a clear example of how to run Vanguas, here we can put in the command line python 3 main.py input. We are prompted with Bango's welcome message as well as instructions for how to input the weights for each of the metrics. We then need to specify the target vector in which the circuit is going to be built in, and the name of the circuit, which is the name of the Verilog file. And lastly, the number of input signals the circuit needs.
We are now going to show example results. This is the example terminal window the user obtains, where we can see the score obtained along with best input signals. We then observe the average score as well as the standard deviation and the starting of the parameter perturbation for each parameter of the best two input signals found. We now see a chart containing which signals were outside of the standard deviation score, meaning they were very sensitive to the Gaussian noise added. Part cost is displayed along with the final data frame containing the average score, the toxicity, the part cost, the assembly cost, and the objective function obtained. The sensitivity plot for the user allows the user to identify which parameters are most sensitive to noise.
Some challenges and failures that we faced were that the simulation was a little less extensive than we had hoped. As we went further into the project, it became clear what we were capable of doing with our knowledge of programming and algorithms. We had originally wanted to use Monte Carlo for the simulation, but it proved too difficult, and we later learned that it was hard to manipulate some parameters because not enough was known. We wanted to add more features such as homology and sticky ends, but we found it difficult to account for computationally, and it was something that was also out of our scope. Originally, we wanted to integrate this with Cello through the use of an API, but we found out that the functionality actually wasn't supported in the current version, and because of this, our tool is more of a localized tool than we had hoped. Some improvements for future developments would be the addition of a GUI for clearer view and ease of use, as well as a better understanding of the capabilities of Cello API and Cello through the request of documentation. Despite the challenges and failures, we were still able to create a functional command line tool. It's able to provide a structure for circuit analysis that uses different metrics than what the API already did. We're able to view things such as part cost linked to the availability and explore failure modes. Our project also provides a base to build upon and add new capabilities and functionalities.